Welcome to Chapter 6 again. Today is the last lecture of Chapter 6, and today we will be talking about models and performance models. So as I was saying, the models that we are going to try to cover, which will be a predictive model, what's the performance of the pavements in terms of fatigue, cracking, and rutting, and other types of distresses, and how can we predict their future performance. So this is here a quote that I got from Dr. Robert Litton. He is from Texas A&M, and I'm just quoting him here when he says performance, because we need to define, when it comes to that definition of, or the term of performance models, you would ask, what is performance? So performance basically is a very general term for how pavement change their condition or serve their intended function with accumulating use. So we really are interested to see what will be the performance of the road in the long run, and how are they performing, and how much distresses and damage are accumulating over the years. So the basic criteria really in developing such models is going to be discussed in this lecture. First thing we need to know is we need to have adequate database built from in-service pavements, and this is really the pavement management system database. We can't really do much of developing any predictive models to predict the future performance of the pavement unless if we have a good pavement database. The inclusion of all variables that significantly affect pavement performance will be included in such database, and therefore we can try to relate the performance of the pavement to the structure of the pavement, to the climate of the pavement, to the how much traffic did I observe at that intersection or at that pavement section, and based on this I'll be able to have a good criteria in developing pavement performance models. Also, while thinking of performance models, I need to think of having adequate functional form of the model. So the model that really has to meet proper statistical criteria for precision and accuracy. I can't just come up with a model and say this is an accurate model, or this is the model that I need to use, and stop right there. I need to provide, for example, what's the performance of the model. Is there any predictions based on this model that matched the true performance of the model? If there is any statistics, does the statistics show that this is a significant model, that it can be used safely to predict the future performance? What's the R-square? What's the amount of variability built in that model? So precision and accuracy criteria is really more or less an error prediction, and at the end of the day you would just look into the coefficient of determination, which is an R-square. So if you have R-square approaching to 1 or approaching to 100%, if it's a percentage, then this means the relationship is very strong and it has a very high accuracy to predict the future performance. On the other hand, if I have a relationship that has an R-square of 0.3 or 0.2, this is a very poor, statistically poor relationship, and it's depending on that, model would be really questionable and it would not be preferred. So while developing performance models, there's two different ways of looking at development of models. The very first one is the deterministic analysis. Basically, is a regression model that can be predicting a single value of something. So if it is based on mechanistic response, it is called mechanistic. So that's why there's two major groups, so deterministic and mechanistic. Another term that we use sometimes, and you would see it in the literature, is called performance-based models. Performance-based models, typically they would use a performance response of the pavement, such as anything related to design, traffic, environment, and those are being used quite drastically by Washington DOT, Nevada DOT, where we would go to the field and measure those traffic information, environmental information, anything related to the design, thicknesses, and then we can come up with a performance-based model. while mechanistic based models, they are really very robust models that they are using now more of a mechanical response of the pavement to relate the pavement life, such as the NCHRP cracking and rutting models. If you Google NCHRP cracking and rutting models, you would see there is a lot of information that was done in the last 10 years or so that really relate now stresses and strains and stiffness. Those are really physical components and physical inputs that we can use to predict the pavement life in a much more accurate way compared to the performance-based models. So let's talk here a little bit about how can I get that deterministic regression analysis. So regression analysis, and so many of you will be dealing with this topic in your career at some point. It's basically a statistical tool that is used to correlate two or more variables together. So once you come up with those relationships are really really perfect in that one variable, for example pavement age, and it cannot be consistently used to perfectly predict another variable such as the pavement condition. It's really very specific and you cannot generalize it. Regression analysis, when you try to come up with several dependent variables and independent variables, you cannot generalize what you've got to another set of dependent variables. So it's really something very local, and it cannot be consistently used to perfectly predict another variable. So the variable, when I say all of the variable is being predicted, which is the y, which is the dependent variable. The variable used to predict the y, which is the x, we call them independent variables. So most of the time we would really be looking into y, and that would be y. This is the response, this is the dependent variable, and now we're looking into an equation which is going to be a function of several independent variables, and that would be x1, x2, all the way to xn. So this is the general form that you would like to see at the end of the regression analysis procedure. So the term least square fit, you would hear it a lot. The term least square fit really comes from the minimization of the square differences between the actual measured data points and the corresponding points that they are predicted on the curve or they are fitted on the line. And let me show you here a visual example of what I'm talking about. So here, this is really a relationship between the x and the y, and I'm trying to come up with the best regression line or regression curve to represent the relationship between x and y. So what we're trying to do in regression analysis is really now to minimize the amount of error between the predicted and the measured. So what does that mean is, as you could see, the true line, the actual data are those points. Those are the actual data. Now, based on the actual data, I need to come up with this trend line, which is going to be used to predict the future performance of the pavement. So how to do this? Again, we're going to go through a mathematical analysis to try to decrease the amount of error. So the error is represented in this equation. This is the true value, which is yn. This is the true measured point, minus yn hat. Yn hat, this is the point on the curve, if we are using the curve to predict y rather than measuring it. So we have fitted points on the curve or in the trend line or the regression analysis line, and the actual data point itself. So based on the regression line, now we need to calculate the coefficient of determination, or what we call the R-square. R-square is simply a measure to tell you how much of the data can be explained by the model. So if I have a perfect fit, that means the model is perfect and is gonna be able to explain every single measured data point. Then that would lead us to an R-square equal to 1. So high values are really preferred, and R-square, again, even somewhere between 0.65 and 0.85 are expected based on so many actual payment management system data. We're not going to get a perfect relationship with an R-square equal to 1, but if we have something between 0.65 to 0.85 and 0.9, that would be really good and good representation. Another adequacy measures for how good is your developed model is the root mean square error, RMSE. This is low values are really preferred to give an indication that this developed model is really good. We also like to do verification sections. Those verification sections are really now are not used to develop the model, but they are going to be used as to develop comparisons of the predicted and the measured performance. So let's say an example, I'm having 100 data points to start with. Typically I would use 75% or 75 points to generate the regression model, and then I'm going to use the rest of the 100, which are 25 points, for verification. So after I develop the model, now I'm going to use the model to predict for me those 25 points and see how close or far am I from the true measure values. So this verification section should be from outside database used to develop the model. One thing also that we need to keep in mind as a measure of engineering, as a measure of adequacy measures, is engineering judgment. We always have to keep this in mind, and we will, and every one of you will establish your own judgment and based on some fundamental engineering checks, just such as, again, payment condition drops with what? So the payment condition will drop with higher traffic or more years. It's never gonna go up. The payment performance, as a reminder, it's this relationship, and it's gonna go all the way down with time. This is time t, and this is here the payment performance. So always is gonna go down with time. If I see something going up, that means there's something is wrong, or there was a major rehabilitation that happened. Also, payment condition drops with severe environmental conditions. If I have a very bad winter and it was lots of snow and freezing and thawing happened to the payment structure, and all of a sudden the payment performance is dropping more and more for that year in particular. So that's also something to keep in mind. As a general rule also, the less the number of variables, the better the applicability. In fact, a significant test should be conducted to eliminate the non-significant variables. So typically at the very beginning we don't know how many variables or how many independent variables, the x's, that need to be included in the model, but the least the better, because now you're really depending on maybe 2 or 3 x's rather than 10, and it would be very hard to come up with an accurate model that has so many variables, because everyone is going to have some inherent variability in it, and therefore the R-square would be less and less. This is here also that we need to think and have it in mind while developing regression analysis models, that we always have limitations on real data. This sometimes we call diagonal problem. What does that mean is, for example, in this case we have traffic. We always have high and heavy traffic, and there's medium in between, and the thickness, the corresponding thickness for the hot mix asphalt is gonna also have to be between thin and thick. So you will always see, and the way you observe in the PMS system, with light traffic we would design our pavements to have a thin pavement, while if I have a heavy traffic I'm gonna always have a thick pavement. So, and that's why you would see your data is really along this diagonal, and very rarely to see a thick pavement that has a low traffic or a thin pavement that has a heavy traffic. So that's also something to keep in mind. Now we're going to discuss some of the existing performance models. One of the big examples, the famous examples, is the Washington State DOT, where they have what they call the payment performance indicator. So the pavement performance indicator that you are using, they call it pavement condition rating, PCR. And you could see this equation now. It's consisting of the summation of D. Summation of D, this is the summation of defect values, which are in the tables that I'm going to show you in a minute, as well as the CPM. CPM is simply counts per mile from a Cox road rater. So once we have those two, and you can read more about it in their website, we will be able to get the PCR. So for this is here table 1 for under their system. Table 1 for flexible pavement defect deductions for PMS. So they have alligator cracking, longitudinal cracking, transverse cracking, and patching. And now they have here how to distinguish between having alligator cracking as well as, is it just a hairline, or does it come with spalling or spalling and pumping. And afterwards you also have to go to this part of the table, which is the percent wheel track per station. So if it's 1 to 24%, then this is the deduct value. If it's 45, if it's 50 to 75%, is 30 rather than 20. And all of those are going to be negative values to be considered in the previous equation. Same thing for Portland cement concrete, deduct the deductions for PMS. Also here we will be talking about basic performance models at the project level. So they have this model or this equation, PCR is equal to C minus M times H to the power P, and this is only applicable for overlays and new constructions. So M and P in the previous equation, those are changed until the best fit is achieved. So the best fit is typically determined by the highest R square and the lowest RMSE. This is here how to get the C and M and P, and they've got 6 equations depend on the case. So once you know C, M and P, you will be able to get the PCR predictions. Those are here the 6 equations. So, and here just to let you know, the equation 6 is more typical of the performance of a thin asphalt concrete overlay. So it's a simple equation, as you could see. It's just 100 minus 1 times H to the power 1. And here you would see the PCR goes from 100 all the way to 80, and the corresponding age or years. Another table under their system, this is the standard default performance equations. You've got one of the locations, Western Washington, and here in the second column you would see the type of construction or pavement surfacing, and then the number of analysis units. Those are the performance equations, and this is the age to PCR equal to 40. Again, this is an example. I'm not expecting you to know more about it, but just to give you an idea what type of models that can be developed. Simple model related to the age right away, rather than a long model that can be hard to understand or not accurate. Table 5, standard default performance equations. That was developed way in the 80s for the Eastern Washington part. Similar format as before. Another example here for the performance models or performance curves is from Nevada DOT. Those models were really developed for both rehabilitation as well as maintenance activities, not for new construction. So when I say maintenance activities, it really included 3 options here: chip seal, sand seals, and flush seals. So when it comes to rehabilitation, it included overlays, road bed modification, all the way to mill and overlay. The attached tables that I'm going to show you in a second gives you a summary of the models. So the very first thing here is the pavement performance indicator, and which is similar to the AASHTO equation. is PSI equal to 5.03 minus 1.91 times log times 1 plus SV, slope variance, minus 1.38 times RD, this is the rotting depth, minus 0.01 times C, which is cracking, plus potholes to the power 0.5. This is here another example. This is table 17 for verified AC overlay for District 2 model. Again, this is just an example. I'm not expecting you to know a lot of information about it, but the PSI equation here, as you could see, is a long equation, and we have several variables, and the variables, they are mentioned here, and everyone has its own range. And the good thing here, we're showing the model, the developed regression model, and how many points were used to develop this model is 154 points, and the associated R-squared is 0.87, which is really quite very accurate. So this is an example here for the models that was developed, the variables that they were used, the ranges, as well as the R-squared and how many data points. So pretty much this is a very good illustration of a one table summary of all the what you need to show when it comes to developing a regression model. Another example here for this is for statewide milling model. So instead of just district, applicable for district, they were able now to come up with one model for the entire state when it comes to milling job. So it's PSI, and it has so many variables, as you could see, and those are the variables along with the ranges, and they used 86 data points to develop this model, and the R-squared wasn't too bad, it's 0.65. Another table here for road bed modification just for District 2. The model, again, it's PSI, and it's in terms of so many variables, including years, and ESLs, which is equivalent single axle load, SN structural number, the maximum temperature, the minimum temperature, as well as, again, here you have the number of observations, 194 points, and R-squared is 0.79. So as you can see, the models were really based on statistical analysis of the field performance data. So the major goal is for you as a payment management engineer to keep collecting data either every year or every other year to have a good and reliable database, which is gonna allow you to come up with an accurate performance model. Those models that can predict pavement performance life based on mechanistic response of pavement structure due to load and environment, those are much stronger. So now we're shifting gears from regression models to mechanistic. Mechanistic are more accurate, as I mentioned before, and they are depending on the true physical performance of the pavement, such as stresses, strains, and stiffness. This is here an NCHRP fatigue model, the National Cooperative Highway Research Program. This is how it stands for NCHRP. One more time, National Cooperative Highway Research Project. And they developed, and they do develop and fund so many multi-million projects to predict the pavement performance. This is one example for fatigue models. If we have fatigue up to 10%, this is the way to predict the fatigue. So the way to do it is log n. N is number of repetitions. So if I know how many number of repetitions of axles or vehicles that's gonna go through the section until I reach failure, then I'll be able to predict the future performance. So as you could see, the model here is depending on two major and dependent variables. Epsilon, which is the measured strain at the bottom of the hot mix asphalt, because fatigue does generate from the bottom of the hot mix asphalt, as well as E, which is the modulus or the stiffness or the strength of the hot mix asphalt layer. So once I know very physical components, which are the strain and the stiffness, I'll be able to predict how many cycles to failure to reach 10% fatigue cracking. Similarly, they came up with an equation that fits up to 45% fatigue cracking. It's very similar equation. All what we changed is just the coefficients here and there, but again we are depending on stresses, strains, and modulus. In this case in particular, we're just depending on modulus as well as strain. So N, as I mentioned, this is the cumulative numbers of easels, how many easels or equivalent single axle loads. Epsilon is the tensile strain at the bottom of the hot mix asphalt layer in microstrains, and E is the resilient modulus for the hot mix asphalt layer and measured in KSI. There is another institute called the Asphalt Institute Fatigue Models. So now they developed this unique model that has now N, which is number of cycles to failure or easels, and it's in terms of, again, epsilon, which is strain, and E, which is the stiffness or the strength of the model or the modulus of the hot mix asphalt. C is another coefficient that was defined later on. But as you could see, again, this can be called mechanistic base model simply because I'm not measuring cracks and other variables from the field. I'm really measuring strain and stiffness and related directly to how many cycles to failure. So the C variable that we talked about in the previous equation is equal to 10 to the power m, and m is as a function of the volume of asphalt, which is VB, and the volume of air voids. Once I know the volume of asphalt and the volume of air voids, I'll be able to predict m, and m now is going to be the power for 10 to the power m to get the C. Another model for rutting, this time not for fatigue. Chevron, which is an oil company, they sponsored some research to come up with a predictive equation for rutting. And rutting also can be related to how many cycles do I need to apply, or how many easels do I need to apply on the street till I reach the maximum amount of allowable rutting. So N here is number of easels, and epsilon Vs, this is basically the compressive strain at the top of the subgrade in microstrain. So this is just a reminder for you that the critical strain that we use for fatigue is different than what we use for rutting predictions. The strain for fatigue prediction is at the bottom of the hot mix asphalt, because this is where fatigue is going to be generated at. While here, for the rutting, we are interested to get the compressive strain at the top of the subgrade, where the rutting, sometimes it's very high at this point, all the way to the surface of the pavement. So also there is another model here that was generated under NCHRP for rutting model. So here it says HMAC less than 6 inches. What does that mean? It means that this model is applicable for hot mix asphalt thickness less than 6 inches. So if I have the top layer, which is the hot mix asphalt, 1, 2, 3, all the way to 5.5 inches, then this model is applicable. Otherwise, I will go to the next page to see the other model, which is, this is here the model that you could see now it's applicable for hot mix asphalt thicknesses more than 6 inches. As you could see in this model, it's predicting or trying to predict the rutting. Those are the variables that I mentioned or that I showed in the previous two slides. RR, this is the rate of rutting, which is 1 times 10 to the power minus 6 inch per repetition. D is the surface deflection. N is the number of 18 kips, which is the easels, times 10 to the power 5. And what's the most important thing, and this is how it makes this model mechanistic, is sigma. Sigma is the compressive vertical stress at the surface base interface. So once I am interested to measure the vertical stress at the surface, between the surface and the base interface, then this I can correlate that to the amount of rutting that happens to the surface. So with that, this was just a summary of some performance models, either regression models or mechanistic models, and that was developed under NCHRP or Chevron or 2 DOTs that we talked about, Washington DOT, and Nevada DOT. So with that, we finish Chapter 6. Thank you so much.